We're constantly hearing about how these massive large language models, LLMs, are getting better at things that seem like reasoning.
Right.
But it makes you wonder, is it truly understanding and thinking? Or is it just like super advanced pattern matching?
That's really the central question, isn't it? A lot of researchers are grappling with that. And while these LLMs can absolutely ace tasks we associate with reasoning, there's still this big debate about what's actually going on under the hood.
Mm-hmm.
So instead of getting bogged down in the philosophy, many are trying to find practical ways, ways to just make them perform even better on these reasoning-related challenges.
Exactly. And that's what's so interesting about the research we're diving in today. It's coming out of the IT University of Copenhagen.
Ah, yes.
And they've taken a really innovative tack, I think, to try and boost the reasoning abilities of LLMs. Think of this as your shortcut, really, to understanding some pretty cutting-edge work happening in AI right now.
Absolutely. Our goal today is to really unpack their approach, specifically how they tackle this challenge of enhancing LLM performance on tasks that seem to require reasoning.
And the paper is?
The paper we're focusing on is called Improving Reasoning Performance in Large Language Models via Representation Engineering.
Okay, representation engineering. We'll get into that. And just so you know where we're headed, our main source is this research paper. It introduces a novel method, a new way to give LLMs a boost in reasoning without that huge time-consuming process of retraining the whole model.
Which is a big deal.
It is. So we're going to break down the problem they identified, the solution they proposed, how they tested it, the key things they discovered, and what it all signifies. So even if you don't have a deep AI background, you'll get a solid handle on this.
Right. Let's start maybe with the problem they're looking at. So as you said, LLMs are great at language, processing it, generating text that sounds human. But their ability to truly reason, that's still a big question mark.
Yeah.
Now, this research isn't trying to, pin down a definition of reasoning in LLMs. That's not the goal here. Instead, it's focused squarely on enhancing their performance. Performance on tasks we typically link to reasoning, things like inductive reasoning, deductive reasoning, even solving math problems.
Right. So less about the deep what is thinking debate and more about getting practical improvements on things that look like reasoning in action.
Exactly.
And what's particularly interesting, I thought, is where they looked for these improvements. Because a lot of past work looked at the final output, right? The answer the model spits out.
That's the common approach.
But these researchers decided to dive deeper into what's happening inside the model itself during the process.
Precisely. Their method falls under this umbrella of representation engineering.
Okay.
Which is essentially a way to try and influence how a model behaves by subtly adjusting its internal state, what's going on internally as it processes information.
Right, manipulating the representations inside.
Yeah. And a crucial idea here is something called the residual stream of an LLM.
Okay, let's unpack that. Residual stream. What is it in simple terms, like an analogy maybe?
Sure. Imagine it like a central river or maybe a busy highway of information flowing through the LLM.
Okay.
As the model reads and processes text, different parts of it, think of them as different processing units or layers. They both read information from this river and they write new processed information back into it. It's this continuous flow. Their paper actually has a figure 1B, that gives a visual for this.
Oh, okay. So it's like all the different components are constantly contributing to and drawing from this shared pool of information.
Yeah.
Makes sense. So how do the researchers actually get their hands on this information flow? What do they do?
Well, they extract what are called activations from this residual stream.
Activation.
Yeah. They grab these while the model is in the middle of working on a reasoning task. You can think of these activations as like the raw numerical signals, the electrical buzz almost, inside the model as it's processing.
So the internal state at that moment.
Exactly. They represent the model's internal understanding or focus at that specific point in processing. And from these activations, they then create something they call a control vector.
A control vector. Okay, that sounds like a steering wheel, a way to steer the AI's thinking.
That's a really good way to think about it. Yeah. This control vector is then applied back to the model. But here's the key part. It happens during inference.
Inference.
Yeah.
That's when the model is actually being used, right? Not trained.
Exactly. When it's answering a question or solving a problem, you give it. So they add this control vector back into that residual stream, that flow of information. And by doing that, they're essentially giving a subtle nudge, hoping to guide the model towards better reasoning performance.
Without retraining.
Critically, yes,
Okay.
without any further training of the model itself. It's like a real-time adjustment happening on the fly.
Okay, that's clever. So they grab these internal signals during reasoning, distill them into a nudge, and then apply that nudge when the model is tackling a new problem. So how exactly do they create these control vectors? Is there just one way?
They actually explored a couple of methods. The simplest one they tried was creating what they called a reading vector.
Okay.
This is basically just an average of all the activations they extracted from the residual stream, but only from instances where the model successfully completed the reasoning task. Equation 2 in the paper describes this, if you want the math.
So it's like taking a snapshot of the model's internal state when it gets it right and saying, hey, model, try to be more like this state.
Precisely. Simple concept. However, they found an even more effective method using what they call contrastive pairs.
Contrastive pairs. Okay.
Yeah. This involves comparing the activations from when the model reasoned successfully with the activations from when it failed. Or, interestingly, sometimes they used activations from when it was just processing random strings like nonsense input.
Huh. So success versus not success, or even just noise.
Right. Equation 3 outlines this. Think of it like comparing the brain activity of someone solving a puzzle correctly versus their brain activity when they're completely stuck or just staring blankly.
That makes intuitive sense. By looking at the difference, you're isolating what's maybe unique or crucial to the successful reasoning process.
Exactly right. You're trying to find the signal associated with success by contrasting it with failure. And to refine this even further, they brought in a statistical technique,
Okay.
principal component analysis, or PCA.
Ah, PCA. I've heard of that. Finding the most important directions in data.
That's the gist, yeah. Imagine you have lots of different factors changing between the success activations and the failure activations. PCA helps you find the single most important direction, the main axis of difference between those two sets of states.
Gotcha.
Equation 4 shows how they applied it. The idea is that this main direction, this first principal component, captures the vector in the model's internal state that most strongly distinguishes success from failure on that task. That becomes their control vector.
Okay.
And just the small technical note they mentioned in the appendix, they initially scale these PCA vectors to have a standard length, and then they adjust that length, or norm, based on the typical size of activations in the residual stream, just tuning the strength of the nudge.
Right. Tuning the nudge. Okay. So they've got their method, derived these control vectors using contrastive pairs and PCA. Now, how did they actually put it to the test? What kind of reasoning problems did they throw at the models?
They used 3 different types of tasks, which is good for seeing how general the method is. First, there was the indirect object identification task, or IOI.
IOI. Okay.
This is framed as an inductive reasoning task.
Wow.
The model has to figure out who received an object based mostly on the sentence structure and patterns.
Inductive.
Yeah.
Like inferring a likely pattern.
Yeah. They used variations like ABA, BABA structures, and longer versions too. An example they give is, Mary and John B. went to the store. John B. gave the groceries to Maria. The model's task is to predict the last word, which should be Mary.
Ah, so based on a ABBA pattern, it should infer Mary received the groceries.
Got it.
What was task number 2?
The second was from a benchmark called BABI, specifically task 15. This is positioned as a deductive reasoning task.
Deductive, okay. Logic-based.
Exactly. It presents the model with a short passage containing some factual statements and then asks a question that requires logical deduction from those facts. For instance, passage. Mice are afraid of wolves. Gertrude is a mouse. Cats are afraid of sheep. Question. What is Gertrude afraid of?
And the answer should be wolf.
Right. It logically follows from the first 2 statements. The third statement is irrelevant.
Makes sense. Deductive. And the third task?
The final one was GSM-8K. This is a well-known data set of grade school math problems.
Ah, math word problems. Always tricky.
Tell me about it. These often require multiple steps of reasoning and calculation to get the right answer. They give an example like, Natalia sold clips to 48 friends in April, then half as many in May. How many clips did she sell altogether?
Okay, so you have to figure out May's sales, 24, and then add it to April's 48 to get 72. Requires steps.
Exactly. Multiple reasoning steps plus the actual math. So yeah, a pretty good range of reasoning challenges. pattern identification, logical deduction, and multi-step mathematical problem solving.
That sounds comprehensive.
Yeah.
Now, how do they actually create those contrastive pairs for these specific tasks?
Yeah.
You mentioned success versus failure or random strings.
Right. So for the positive examples in the pair, it was straightforward. They used instances where the model successfully answered the question correctly.
Okay.
For the negative examples, it was a bit more complex. They actually tried a few things. One idea was prompting the model to explicitly give a wrong answer, but apparently that didn't work very well. Another approach was using examples where the model just naturally got the answer wrong during its normal operation. But the issue there was sometimes the wrong answer wasn't completely illogical, just not the specific target answer they wanted.
I see. Not a clean failure signal.
Exactly. So interestingly, they found that using just random strings of characters as the input for the negative prompts actually works surprisingly well.
Just random noise.
Yeah, it seemed to provide a good baseline, non-reasoning or confused internal state to contrast against the successful reasoning state.
That's really interesting.
Okay.
That noise is a good opposite to reasoning.
Yeah.
Okay, what models did they run these experiments on?
They primarily used models from the Pythia suite, developed by Eleuther AI.
Ah, the Pythia models, known for being good for interpretability research.
Exactly. Specifically, they used Pythia 1.4b and Pythia 2.8b, which let them see if the technique scaled with model size, at least in that range.
Okay.
And importantly, they also tested their approach on Mistral 7b Instruct.
Oh, right. Mistral 7B, that's a much more capable model, and instruction tuned too.
Yes, significantly larger and generally performs much better out of the box. So testing on that gives a better sense of relevance to more modern systems.
Good point. And where in the model architecture did they usually apply these control vector nudges? You mentioned the residual stream runs through layers.
Right. Based on prior research in this area of representation engineering, they typically applied the control vector to the middle layer of the transformer architecture in these models.
Middle layer. Okay.
Seems to be a common finding that manipulating middle layers can have significant effects on high-level behaviors.
Makes sense. And how did they actually measure if this nudge was working? Did they just check if the final answer string was exactly right?
Well, they did look at exact match accuracy, especially for the GSM-8K math problems where there's usually one precise numerical answer.
Okay.
But for the IOI and BabyI tasks, particularly in what they call zero-shot scenarios where the model hasn't seen examples of that exact task format before, they focus more on the probability, or technically the logit, of the correct token being generated.
The logit, so like the model's internal confidence score for the right answer.
Sort of, yeah. It's the raw score before it gets converted into a probability. They looked at the logit assigned to the correct answer token, often within a predefined set of possible correct answers. The idea is that smaller models especially might give a verbose answer that contains the right word, but isn't an exact string match.
Ah, so like saying the answer is Mary instead of just Mary.
Exactly. Looking at the logit for Mary is less prone to being thrown off by that extra text compared to just checking if the whole output is Mary. It measures if the model was leaning towards the right concept.
Okay, so focusing on the likelihood the model was on the right track internally. Smart. Now let's get to the juicy part. What were the key results? Did it work?
Okay, results time. For the smaller Pythia models on that IOI pattern matching task, they did see slight improvements in accuracy when they applied the control vectors. You can see this in figures 2A and 9A in the paper.
Slight improvements. Okay.
And interestingly, this small improvement seemed to generalize across the different variations of the IOI task. Generally, yes, lower entropy means the model is more peaked, more certain about a particular answer. And they found that entropy slightly decreased when the accuracy improved with their intervention.
Which is what you'd hope for. Better reasoning leads to more certainty in the correct answer.
Ideally, yes. A nice confirming signal there, even if the effects were modest on Pythia.
Okay, so a little nudge internally led to a bit more accuracy and confidence for Pythia on IOI. What about the larger, more capable Mistral model? How did it do on the Bibabi deductive task?
Right, moving to Mistral 7b Instruct on BB. Here, they saw more significant improvements in accuracy with the intervention. Figure 3A shows this quite clearly.
More significant? Good.
The KL divergence, measuring the change, again showed this kind of quadratic increase with the strength of the nudge. Bigger nudge, much bigger change.
Okay.
But there was something a bit unexpected with the entropy for baby on Mistral.
Oh.
They noted a slight upward trend in entropy as accuracy improved.
Wait, upward. More uncertainty, even as it got more accurate. That's weird.
It is a bit weird, yeah. They acknowledge it was unexpected. Usually you'd think better performance means lower entropy, more certainty. So that's a curious finding for baby.
Hmm, okay. And what about the math problems? GSM-8K on Mistral. That seems like a much tougher nut to crack.
It absolutely is, and this is where it gets really interesting, I think.
Oh, yeah.
They found that their intervention technique did improve Mistral's ability to solve these multi-step math problems, but often the improvement happened when they used a negative alpha value.
Negative alpha. So they were nudging the model's internal state away from the success direction they derived.
Exactly. Pushing it in the opposite direction of the calculated control vector actually helped it solve math problems correctly more often. Figure 4a shows this.
Whoa, okay, that's seriously counterintuitive. Why would nudging away from success help? Any ideas?
They don't offer a definitive explanation, but it suggests the relationship between internal states and correct reasoning for complex multi-step tasks like math might be, well, more complex than for simpler tasks. Maybe the successful state they captured wasn't the whole story, or maybe pushing away from it prevents some kind of common failure mode. It's fascinating.
Definitely fascinating. A negative nudge helping with math.
Wow. And the KL and entropy trends for GSM-8K.
Also different. Unlike the other tasks for GSM-8K, both KL divergence and entropy seemed to increase together as performance improved, showing a positive correlation. So more change and maybe more internal exploration or uncertainty was associated with getting the math right.
So the internal dynamics seem quite different for math versus the other reasoning tasks.
It certainly looks that way based on these results.
Okay, but there's another result I remember seeing that really jumped out, something about generalization across different types of tasks.
Yes, this was, for me, one of the most surprising and potentially very important findings in the whole paper.
Tell me more. They discovered that a control vector trained on the baby I task, remember, that's the deductive reasoning task, could actually improve Mistral's performance on the GSM-8K mathematical reasoning task.
Wait, the logic vector helped with math?
Yes, and vice versa. A control vector trained on the GSM-8K math problems also improved performance on the baby I deductive task. They show this in Figure 5 and Figure 11 in the appendix.
Wow, okay, that is surprising. So the nudge derived from doing logic helped with arithmetic, and the nudge from arithmetic helped with logic.
Exactly. This cross-task generalization is really suggestive. It hints that maybe these models aren't just learning task-specific tricks. Perhaps there's some shared underlying mechanism or representation related to more general reasoning that these control vectors are tapping into.
So it's not just an IOI reasoning module and a separate Betty I reasoning module. There might be something more fundamental.
That's the implication, yeah. It suggests that the internal state changes associated with success in deductive reasoning share something important with the state changes for success in mathematical reasoning, at least in this model.
That could be huge.
Hmm.
It opens up the possibility of maybe training or nudging for more general reasoning improvements, not just task-specific ones.
Precisely. It's a very exciting finding.
Did they look at how the intervention changed the model's output, like qualitatively?
They did. For Mistral on the GSM-8K math problems, they provided some examples in the paper, Figure 6 specifically. They showed cases where the model initially got the answer wrong, but with the intervention, the control vector nudge, it produced a correct answer.
And how did the reasoning process change?
Sometimes the interventions seem to cause the model to generate a slightly different reasoning trace. It's step-by-step thinking. In one example, it seemed like the nudge caused it to add a small but crucial intermediate calculation or piece of information that it missed before, which then led to the correct final answer.
Ah, so subtly guiding the chain of thought.
Kind of like that, yeah. It's not giving it the answer, but maybe nudging the process. Of course, they also showed examples Figure 8, where the intervention unfortunately pushed the model towards an incorrect answer.
Right, so it's not a perfect magic bullet. It can help, but it can also potentially hinder.
Exactly. It's influencing a complex system, so the outcomes aren't always predictable or beneficial. But the fact that it can systematically improve performance by subtly altering internal states is the key finding.
Okay, so stepping back now, looking at the whole study, what do the researchers themselves say are the main takeaways? What do they see as their novel contributions here?
Well, their primary novel contribution, as they stated, is really this direct analysis of improving what we perceive as reasoning in LLMs, using this specific technique representation engineering applied to the residual stream.
So directly targeting reasoning via internal states.
Yes. And they've shown pretty convincingly, I think, that this residual stream does contain valuable, actionable information about the model's reasoning capabilities, information you can extract and use. Furthermore, a big point they highlight is that reasoning performance, or at least performance on these reasoning tasks, can be modulated or controlled in a way that's similar to how other researchers have controlled other model behaviors.
Like what other behaviors?
Things like controlling the sentiment of generated text, or making a model better or worse at playing a specific game, or even inducing specific factual recall. These have also been influenced using representation engineering.
Ah, I see. So they're saying reasoning isn't some completely different, untouchable thing. It might be another behavior encoded in the model's representations that we can potentially spear.
That seems to be the suggestion, that the ability to reason, or at least to succeed on these tasks, might be encoded in the model's internal state in a way that's kind of analogous to these other learned capabilities.
That's a pretty significant claim. It makes reasoning seem less like a black box mystery and more like a potentially understandable and modifiable aspect of the model's internal configuration.
It does lean in that direction, yeah. It's quite a shift in perspective.
Now, of course, no research is perfect. What did they acknowledge as the limitations of their own study?
They're upfront about a few things. First, they acknowledge that they primarily worked with models like Pythia and Mistral 7B, which, while capable, are smaller than the absolute current state-of-the-art giants.
True, like GPT-4 or Claude 3.
Right. Though they do point out fairly the interpretability benefits of the Pythia suite and that Mistral 7B is a very respectable and widely used model.
Okay.
But also note that the IOI task, while useful for their initial explorations, is relatively simple and might not fully capture the complexities of more general real-world reasoning.
Fair point.
And they also reiterate that they focused on improving performance on tasks associated with reasoning without trying to definitively say they've captured or defined reasoning itself.
Keeping the scope focused.
Yes. And finally, they mentioned that their work on creating these contrastive pairs, specifically for reasoning, especially using things like random strings, represents fairly initial steps. More research is definitely needed to figure out the optimal ways to derive these console vectors for enhancing reasoning abilities.
Yeah. So a promising start clearly demonstrated the potential, but also highlighted clear avenues for future work and refinement.
Exactly.
Okay.
Yeah.
So to wrap things up then, what's the big picture here? If someone listening wants the main takeaway from this deep dive into their research, what should it be?
I think the core takeaway is this. It seems possible to make subtle adjustments to the internal workings, the representations inside these large language models, and by doing so actually improve their performance on tasks we associate with reasoning.
And critically, without retraining.
And critically, without that incredibly costly and time-consuming process of retraining the entire model, that's a huge practical advantage. And beyond that, the really surprising finding of cross-task generalization logic helping math helping logic, hints that there might be a more generalizable reasoning signal within these models than perhaps we previously understood.
Yeah, that cross-task result really sticks with you. And it leaves us with a pretty thought-provoking question, doesn't it?
Mm-hmm.
Could this method, this ability to subtly influence an AI's internal state, pave the way for building AI systems with more controllable, more reliable, maybe even more understandable reasoning processes?
That's the big question hanging in the air, isn't it? And it also raises other questions, maybe ethical ones, about being able to nudge an AI's cognitive processes, so to speak.
Definitely something to mull over.
Indeed. And for those of you who want to dive even deeper into the technical side, the researchers have made their paper and, importantly, their code publicly available on GitHub.
Oh, great.
Yeah, it's a fantastic resource if you want to understand the nuts and bolts, or if you're interested in maybe building on this research yourself.
Excellent. We will absolutely make sure to include links to the paper and the code in the show notes for anyone interested. This is fascinating stuff.
It really is an exciting direction for AI research.
Thanks for walking us through it. And thank you for joining us on this deep dive.